Today we'll be working on homework 2 part B. The first question is to derive the time-dependent heat diffusion equation for a uniform linear bar assuming constant thermal diffusivity. So I'm just gonna give us a little bit more room for me to show this. Well, we start here. And then jump right into things. That's upside down. Okay. So we're going to start with a bar. I never claimed to be good at drawing. Apologize for that. That would be it, right? Yeah. And then we want to cut out just the space of this bar. So this bar will have a area, a specific heat. I believe there's one thing else, but we're going to talk about this bar and like how this section is x or dx. And if we cut out that section of that bar, we can look at the flow rate going through that bar, as well as the distance going through that bar. Excuse me. Which, as we're going through this would be Q plus Q, or plus dx, if I remember correctly. And then we can look at from point A to point B of this section as x and x plus dx. The other thing that I believe that I'm missing is that for our bar as a whole, we will also have a density, which is not Q, it's rho. And then we will get into the energy balance. In 1 second. So with our energy balance, we know that this is true. Well, if we look at what we have here versus here, is that mass can be changed into density times volume. And then, because we don't have a volume based off of what we've shown here, we can change the volume to area times dx. Ooh, area times dx. And then we can also change our temperature to initial to reference temp, which this really goes to 0, so we're not too concerned about it right now, to just leave us with density times area dx, heat capacity times T. And with this, we're looking at the temperature in respect to time. So we can write it like this. Now let's take a look at the other side of this equation. We know that Qx, which I missed over here originally, But we have, for this other side, we have Qx going in minus Qx plus dx going out. And then we know that Qx can be equal to, where do I want to write this? Qx can be equal to negative k, which is our thermal conductivity times area times dt over dt, or not in respect to time, respect to area, sorry. And then we also know that Qx plus dx can be equal to Qx plus dqx over dx. Oh, I'm running out of space, but we'll just put it like this, dx. So now we can take this and plug it back in here, which would give us something, Qx I feel like I'm missing something. Please, 1 sec. But we can substitute this first one in here, which would make this flow plus dx, which then we can take these, they'll cancel, and then we can substitute in the thermal conductivity dt over dx. Where are my equal signs? And then the only thing that I'd be missing is that this one would be squared. I believe. Okay. Now I know that we can cancel stuff out. So our areas cancel, our dx's cancel. On that side, I think everything else stays on the other side. Let's see, dt over dt. Man, I wish I could shake this cough. But we can also see that after we move these over, we can see that this looks like alpha, which we've seen maybe not in this class, well, maybe not earlier in this class, but alpha is our thermal diffusivity, which is a constant Okay, now we can move to question 2, which is express the heat diffusion equation from part B1 as an algebraic equation via backwards explicit differentiating. So we will need to go back and look at our diagram and split it into a few more of these cubes, just so that we can look at each one. We're going to look at n plus 1, n minus 1 for each of the cubes in succession. And then we also want to look at the areas in between them. So we're going to make these J, not going to have enough room, well, that one I will. So just remember that this is x plus dx, and then this will be J minus 1, this will be J plus 1, and then we need to think about this, but in terms of here, our equation we found in part 1. So I'm going to rewrite this, just so we remember it's important. Alpha t squared t dx squared is dt over dt. And that we need to we'll look at the right hand side of this first, just because it's a little bit more self-explanatory. But over dt, we know that that will be over whatever time. And then to look at the difference in temperatures, we need to look at the difference of temperatures from T n minus 1 J to T n J, because we want to look at in between these two blocks, this specific section. And I'm now realizing I'm probably going to have a lot of issue writing everything else here, so we're just going to move all this over. For the time being, because this side gets a little messy, so we're going to leave this alpha just kind of stranded off into no man's land for right now. And then, how do I want to do this? We're going to move this, you know what, we'll just keep pushing this down. So we'll remember this, but we'll just push it down every time that we add a step. Same with the alpha. Just because I think it will be a little bit easier for us that way as we move through everything here. I just don't want to get too mixed up with my work. So we need to look at this top half first, because since it's the double derivative, let's look at just the first derivative for each one, which the first derivative dt dx, and then dt dx. And since we're looking in between, we're looking here for n plus 1, this one would be j plus, j, one is j and one's j plus 1, be j plus 1, on this side. I think. Wait, we're looking at which section? I'm getting myself confused. Just give me 1 second, please. Okay, I'm losing it. We're looking at J minus 1. And then they're both over dx. So now we need to take these guys and separate them out for each one. So we'll have t of j plus 1 minus t j all over delta x there. And then for the other side, we would keep the ends. And j minus 1 and delta x, and then everything will be over delta x. So now we can start to simplify this, which we'll have delta x squared, and then plus 1 minus tn to the j minus t j plus tj minus 1 to the n. I'm just gonna check that real quick before we move on. Okay, so now, since this is right, we will bring everything back down just to make everything all fine and dandy. And then we have common terms here. And we will also, it said explicit form backwards. So with that, then we will need to single out this term. So we have alpha over squared delta t times t j plus 1 and minus t j n. Oh, I made a mistake. We also missed this term. Remember that this goes here. And then that should be our final equation. As we get into the code, we will see this, but this term is equal to r, and r has to be lower than 0.5, which we will look at more so in the code. But this statement is stating that if you look back at our block, can you see the whole thing? But if you look back at our block, our change in, if we look at bigger steps of time, we will also have bigger chunks over time, and if we look at bigger distance intervals within our bar, time will go down. Okay, I've already moved this camera. I'm just gonna get everything else set up, and then we'll be right back for part B, question 3, I believe. Okay, so now that we're back, we can do question 3, which is simulate the time-dependent response of a uniform bar initially at 50 degrees Celsius after its ends are raised, then maintained at 40 and 80 degrees Celsius respectively, and discretize the bar into 20 sections and show the simulated results for R at these two R values. So we can start out with everything that we start before. I'm just going to steal everything from before. And then we're also going to need one more, which is, if I remember, set point options. Python. Maybe that's not what it is. Give me 1 second to remember what it was. Okay, so it wasn't set point, it was set print. So then it would be np.set print options, and then we want a precision of 1, and then what was the other one? Line width equaling 100. Equaling 100. If that all runs, then we should be fine. Which we're good there. Then, we need to 20 sections, 50 degrees C. So we would need to first make an array of temperatures, which we can use with NumPy full, which we need 20 spaces, and we want to fill it with temperature 50. Ooh. There we go. So now we have 20 sections with 50. We'll also want to, our ends are 40 and 80 respectively. So this should be 40, and then -1 should equal 80. And then if I print T again, then it makes the first and last T. And then while we're here, we can we'll print T. And we'll make R equal 0.5 to start. I don't know if that's useful yet, but it's the only R. Yeah, because we will now need to make a what's it called? Subplot. So in order to do that, we'll do it just like we have in the past by making a figure. And then we will add a scatter plot. And then we'll make both the x and y values equal to the temperatures, or no, that would give us a straight line. I want just the size of like 140, 250, so on 50, and then 2080. How? 1 second. Let me figure out how to do this properly. Okay. So my x's would need to be NP arranged size of our thing. So I believe it's make square subplot, and then there's no need, and then fig dot scatter plot. I think it's just scatter. Add scatter. Add scatter plot, and then x and y's. So x would then equal np dot range dot t, I think is how it be right, and then y equals t. No. T dot size. Oh, it's less. Sorry about this. Oh, I put 2 R's. There we go. So we start at 40. By 1, we're up to 50. Then we jump to 80 by the end. Now we need to add. Excuse me. Okay, so now we have to add our equation. Might have said that before. Took me a second to figure out where I need to go next. So for I, because we're just going to index and is that the correct formatting? Man, it's been a while since I've done this. You want to take T1 -1 and then make that equal to learn to type. There we go. just use, or was it plus? Yes, it was. Plus R times T index of 2. And we can leave that open because it will just go to the end, which is a very nice feature. And then we want to do minus 2 times T, well, actually, oh wait, those should be negatives, that I do know. 1 to, beginning to end. And then we can plus T, and then start to finish. And then for each time that runs, we want to run for I is in, I forget the correct, I think it's this. By all the red lines, it's mad. Can I look at it now or no? But then for each time, I want it to add to the scatter. It's mad. Yeah, I knew that syntax was wrong. Give me 1 second. And I'm just having it this morning, aren't I? I don't want for, I want if. If I is divided by 100 is equal to 0, then this. So that should make it 10 times every 10 iterations. For loops, how do for loops? Oh, is it in range? Is that what I missed? Range. I was defined up here. Why are you mad about it? Not what I expected. Okay, gotta come. Okay, so now we have to figure update layout, and then we want to oops. Now it's full screen. Height, width, 100. If I refresh this, refresh this. Now we have what we're looking for. So with that, then we can start to change our R values, I believe, and show the simulated result for R. .495. So in R is 0.495. We're good. But if we change it to 0.505, we would then get a very wonky graph, which in part 4 we will explain this, but let me get these side by side for you. I know I did it here. Row 1, column 1. So I'll make this a 2 row. 1 row, 2 column. Then here, we'll do 1 by 1. Equals column equals oh, I put them in an array. That's not how that was supposed to work. There's 1, and then let's actually take this whole thing. I'm going to put it in the same one so then it runs. But this will make 495. And then we'll make this one 505. Then every time we run it, that didn't do what I wanted to. Row 1, column 2. There we go. Now you can see the difference in between the two. There we go. Now I'm going to quickly transition to go back to the board because the last question is using von Neumann stability analysis. Explain why simulation results are unstable when R is set larger than 0.5. So in order to do that, I'm going to change my screen and all that so then you can see the board better. So in order to show this, we need Euler's equation, which I believe is e to the I x equals cosine x plus I sine x. And then with this, as you modify up here, you can modify with inside the cosine and sine. Let me double check that real quick before I give false information. Yes, so with that true statement, we want to then look at temperature as a whole, which temperature, we want to look at the equation we had before, which had the alpha value in it. Or not yet. I'm gonna look at alpha x squared, or k squared, sorry. K squared minus e to the negative kx. I believe. Or not negative, ikx. And how that compares to the equation we had earlier, which was times alpha. And that's what we're really looking at right now for this last problem. So since we know that t is equal to this, and we have this, we're going to need dt, and then dx dt, and that's only to get us to, or not, what am I doing? Getting ahead of myself. D squared t over dx squared, and then, or to get to this. So this first one, we have e to the negative alpha k squared t. This is product rule, isn't it? Derivative in respect to time. No, it's not. This is quotient rule, or not quotient rule. This is a constant because we're doing it in respect to temperature, or temperature in respect to time. There's no time here, there's time here. So then we'll also have to multiply by negative alpha k squared. And then here, if we do it in terms of x, we have our constant, and then it'll be multiplied by the same times ik. Not t. X. I'm missing something. I'm doing something wrong. Multiply by x. I was right here. The constant would be pulled out front. And then here we would keep the constant again. Which, you know that I is equal to this. So if we square I, we square this. We'll just have -1. So then, due to this, we're just going to take this and make it negative k squared. These would have I squared and k squared. So it would be whatever k squared is, negative. Okay. This is where it's going to get really messy really quick. So we're looking back at this big mess. So we have our first constant, no need to worry. So we need to find these 3 terms based off of all the stuff we found up here. So I'm gonna just write out the terms we need. All separately here. And then we'll find them all, and then we can plug them all in here momentarily. So t to the n, the j plus, and I'm gonna probably not go in the order I wrote them down, just because of what makes sense in my head. So to the t to the n subscript j is just gonna be what we had found earlier, which is e to the negative alpha k squared t e to the I kx. E to the I kx. But earlier we had found that this, if we substitute in things, we also have n delta t and I k j delta x. So that would be that one. And then now we can look at and the one above it, which we have t j to the n. We know that we need that, which we have already found. And then let me stand back up. My hand is cramping from holding this phone. T to the n j1 e to the t to the j, so now we need the plus 1 portion of it. The plus 1 portion would be just I k j, which we have, so delta x. So now we need the minus version of it, which would be here. Oops. E to the negative x delta tj to the n, and then I think I wrote letters incorrectly somewhere, because this n minus 1 I think was supposed to be a plus 1 from earlier. TNJ, TNJ, TJ minus 1, TJ. This should be a plus, this should be a plus, I believe. Which, this would be E. Okay, T. Alright, not T, but delta T. Here. And then the plus 1 from that is the plus 1. And then we can just do T and J. Because this is plus 1. This is minus 1 for the j. Because we have here, we have n and j in terms of each one. That's the original, and then this would be plus 1 for j. And you might be wondering where this j and this n are going in each one of these. It's because it's pulled out in these terms. Let me check all these before I keep moving on, but I believe the next step would be to just take these and plug them into here. So now we can plug, and we have R, and then j plus 1, x, tjn, tjn. And then we can pull out the TJN out of here. So I'm just going to do that this way. And write it over here. Then we can pull the TJN out of both. But let's simplify. Actually, let's inside first. So inside we have Euler's law, which we looked at up there, because this would come into 2 cosine k delta x minus 2. Then we can pull out TJN to get R plus 1. Or I'm going to take 2 steps here. I'm also going to pull this 2 out. So then we have 2R times cosine k delta x minus 1 plus 1. So you'd have TJN plus 1 equals TJN times 1 plus 2R plus 2R cosine k. I'm missing something. That's good. That's all good. No, I'm not. Okay, we're fine. I'm plus 1. Then we know, if we look at this, it has to be less than or equal to 1. And then we can slowly do our math here with the 2 separate sides of positive or negative, if I remember how to do this properly. want to look at -1 of all of this. That's not an A. It turned into an A very quickly. It's delta x. Delta x. 1. And then if we take this 1 out, we can look at 0 and -2. And then our next step would be, I lost at -1. Minus. Then I believe we'd want to divide by 2. To get -1 r, not 2. Divided by 2, still 0. And then we know that this would be equal to -2, so then you'd have -1, oops, sorry, r -2, which would then get us r has to be less than or equal to 1/2. And then be it.